Good morning, students. Today's lecture focuses on refrigeration of milk, which is one of the critical preservation steps in dairy technology. Refrigeration is not merely cooling, it is a scientifically controlled method to inhibit microbial growth and preserve raw milk quality from farm to plant. In this session, we will examine objectives, temperature zones, refrigeration principles, cooling systems, cold chain management, advantages and limitations. Let us begin with the introduction to refrigeration of milk. The primary objective is to arrest bacterial growth and preserve the natural quality of raw milk immediately after milking. The target temperature is 4 degrees Celsius. Milk must be cooled rapidly to this level to extend shelf life. The time constraint is critical. Cooling must be achieved within 2 to 3 hours of milking to prevent spoilage. Temperature and time together determine success. Why is cooling raw milk necessary? First, to prevent spoilage. Rapid cooling inhibits multiplication of microorganisms. Second, to control enzymes. Cooling slows enzymatic reactions that cause off flavors and chemical deterioration. Third, to maintain a critical limit. Milk must reach less than 4 degrees Celsius within 2 hours of milking. This is a scientific standard in dairy operations. This slide explains the effect of temperature on microbial growth. There are 3 temperature zones. Safe zone, 0 to 4 degrees Celsius. Bacterial activity is minimal or significantly slowed. Psychrotrophic zone, 4 to 7 degrees Celsius. Cold-tolerant bacteria grow slowly and produce heat-stable enzymes. Danger zone, 10 to 45 degrees Celsius. Rapid exponential microbial growth occurs here. Milk can spoil within hours. Therefore, refrigeration keeps milk within the safe zone. Let us understand the principle of milk refrigeration. The vapor compression refrigeration cycle operates in 4 stages. First, compression. Low pressure vapor is compressed to high pressure and temperature. Second, condensation. Heat is rejected to the atmosphere and vapor becomes liquid. Third, expansion. Sudden pressure drop causes rapid cooling. Fourth, evaporation. Refrigerant absorbs heat from warm milk, reducing its temperature from approximately 37 degrees Celsius to 4 degrees Celsius. This thermodynamic cycle enables controlled cooling. Cooling methods at farm level vary in efficiency. Can immersion is traditional method. Milk cans are placed in cold water. Cooling is slow, taking around 3 hours to reach 15 to 20 degrees Celsius. Plate heat exchangers allow pre-cooling. Milk flows against cold water across metal plates. Cooling is faster and more efficient. Bulk milk coolers are modern systems. They use direct expansion refrigeration and cool milk rapidly to 4 degrees Celsius within 2 hours. Among these, bulk cooling is the most reliable method. Bulk milk cooling systems include 3 major types. Direct expansion systems. Refrigerant evaporates directly in the tank jacket. Highly efficient but risk of freezing if milk volume is low. Ice bank tank systems. Ice is formed during off-peak hours. Chilled water circulates to cool milk. No risk of freezing. Glycol chiller systems. Propylene glycol is chilled and circulated. Provides instant cooling and maintains quality, though initial cost is higher. Selection depends on farm size and investment capacity. Cooling at collection centers follows a structured workflow. Step 1. Reception and quality check. Platform tests such as organoleptic, COB and alcohol test are performed. Step 2. Instant chilling. Bulk milk coolers or plate chillers reduce temperature to 4 degrees Celsius. Step 3. Buffer storage. Milk is stored under controlled low temperature. Step 4. Insulated transport. Milk is transported in tankers to the processing plant without thermal loss. Each stage includes quality checkpoints. The role of cold chain is critical. An unbroken temperature control system must exist from farm to retail. At the farm level, immediate cooling within 2 to 3 hours. At the collection center, bulk storage at 4 degrees Celsius. During transportation, insulated tankers maintain low temperature. At the processing plant, milk is received at less than 4 degrees Celsius, stored, pasteurized and chilled again. The core principle is the cold chain must remain unbroken. Rapid cooling offers multiple advantages. Microbial quality improves. Reduced bacterial count lowers standard plate count. Shelf life extends. Delayed spoilage allows longer storage and transport. Nutrient retention improves. Vitamins and natural enzymes are preserved. Economic benefits arise. Farmers receive premium prices for low bacterial milk. Processing suitability improves. High-quality milk performs better in cheese and butter production. Despite advantages, challenges exist. High power consumption increases operational cost. Rural electrification gaps cause cooling interruptions. Maintenance requirements demand skilled technicians. High capital investment limits adoption among smallholders. Cold chain breaks during transport can compromise quality. Thus, infrastructure and economic factors affect implementation. This slide provides a visual summary of milk refrigeration. At farm level, cool milk from 37 degrees Celsius to 4 degrees Celsius within 2 to 3 hours. Primary methods include bulk milk coolers and plate coolers. During collection and transit, maintain temperature at 4 degrees Celsius. Monitoring systems such as GPS and temperature logs ensure integrity. At plant level, milk is received at 4 degrees Celsius, stored, pasteurized, and chilled again. The core principle is the cold chain must remain unbroken. To conclude, refrigeration of milk is a critical control measure for maintaining microbiological quality and economic value. Cooling inhibits bacterial growth, but it does not kill bacteria. Pasteurization performs that function later. Therefore, refrigeration is the first defense in milk quality preservation. Thank you.